Okay, hello everybody, and welcome back to this week's video. So last week, as I'm sure those of you who watched the video will remember, we derived successfully from Maxwell's equations and the fact that we need invariance between reference frames. We derived the Lorentz transformation, which is that for which the speed of light is constant under all reference frames. At least that's how we came up with it last week. We equated the two forms of the wave equation with these coefficients, and yeah, we ended up with the Lorentz transform, which says that the new time is this gamma, that being 1 over root of, or other, yeah, 1 over the root of 1 minus v squared over c squared, brackets times the original time minus this v over c squared, which that v being the velocity and then x being the position, and then this expression for the new position under various reference frames. Now we're going to look into consequences of, and specifically we'll begin with time dilation. So if you remember last week, we had our original reference frame S and our new one S dash. So what we'll first do is we consider a clock at the origin of S dash. So X dash there is 0. It ticks at some time t1 and time t2. So we have a proper interval. So if we have our clock at S origin, where x equals 0, and then it ticks at t1 dash and t2 dash, therefore delta t dash is equal to t2 dash minus t1 dash. I need a better audio interface. This one keeps making strange noises. Anyway, so we can just invert the transformation here to find the original times between these. So we have that t1 then is gamma t1 prime, t1 dash even, plus our x is 0, x prime is 0 rather, and then c squared, and then that's just gonna, because times 0, so this is simply gamma t1 prime, and t2 is then also gamma t2 prime. So that gives us a delta t of gamma times t2 prime minus t1 prime, which is just gamma of our delta t prime, that being exactly the same thing we have there. So that's interesting. First of all, right, that we can at least say a few things here. The first thing is that gamma is greater than or equal to 1. So if delta t is some factor, some multiple of delta t prime, that means that delta t is greater than delta t prime, or equal to, in the case that gamma is 1. What does that mean? Well, our time interval in our initial frame, just S, is greater than the time interval in S dash. So our moving clock, our clock in S dash, is measured slower than in S. The clock in motion ticks at a rate that is reduced by this factor of gamma relative to our stationary clock S. And that's essentially Einstein's principle of time dilation. So if you have, it's at very minute levels, it's very, very close to 1 at low speeds, but of course, as gamma, as v increases, gamma is going to increase, and so this time dilation becomes more noticeable as you're moving at a faster speed. And you can just look at that by analyzing the variables in gamma, because of course it's a fraction. So it's going to be, you know, if you even just look at it, it's 1 over root 1 minus c squared over v squared. So as v decreases, v squared decreases. As v increases, sorry, v squared increases, so that whole fraction decreases. So 1 minus that fraction is going to increase, so the root of that is also going to increase, and then it decreases. I got that the wrong way around. Sorry. As v squared increases, that fraction decreases. So 1 minus that fraction increases. So a higher number square root is going to be a higher number. So 1 over that decreases. That's not what was in my head 2 seconds ago. Why am I... Oh, it's 1 over v squared over c squared. Ooh. Would help if I wrote down the right thing. So that increases, that whole fraction increases, 1 minus that decreases, so that square root decreases, so 1 over that increases. Yeah, okay, cool. So here we can pretty clearly see that then gamma is proportional to v. Not directly, but it's proportional to v. So yeah, or more accurately, proportional to, as v increases, gamma increases is the important thing out of here. So as you get a v that's very close to c, this fraction, of course, will become closer and closer to 1. So this will become closer and closer to 0. So the square root of 0, and then it will become closer and closer to infinity. Obviously, that's unattainable, but the principle still stands. So yeah, that's how we get our principle of time dilation. I'm going to draw a little line there, and then I'm going to do another one, because we're going to look at the, I guess, the second main principle of general relativity. Let's do rods. Let's consider a rod at rest in S prime. So we have a rod in S dash with endpoints x dash 1, x dash 2. So x1 dash, x2 dash. This is our rod. It's literally just a rod. And yeah, so it has a length. So we have length LO, that being the initial, length being x2 dash minus x1 dash. Now let's measure that in S and see what happens. So again, we can plug things into the Lorentz transformation using our x formula respectively. So x1 dash is gamma x1 minus vt, and x2 dash is gamma x2 minus vt. And that's literally just from plugging it in. So we can then establish a difference between these. So our new L, in fact this will be L naught, the difference between these two, is that minus that, and then that would become positive, so the gamma vt term would cancel out, so it would be gamma x1 minus gamma vt minus gamma x2 plus gamma vt, because 2 minuses, and then so we end up with gamma x1 minus x2. It should be x2 minus x1, I realise. x2. My head is clouded up with Mao's China history knowledge, and I'm more focused on that than on length contraction. It's alright, we'll get through. And of course this is just going to be our length L that we observe, so L naught then is gamma L, and to put it into the form we had above, L is L naught over gamma. Now importantly, length contraction, this means that L, or rather therefore L, is less than or equal to L naught That is what we get out of this. And in the same way that time dilation is only really apparent at very high speeds for the exact same reasons as that, length contraction is only apparent at very high speeds, but it does happen. And it's very interesting, and this is where they got the ideas from. So yeah, and again, you can calculate how much exactly something will contract by at some speed by using the gamma, and just literally plugging in your values to gamma. Now, yeah, we can look at relativistic velocities. This will require a bit of calculus, but it's not too bad. So we have an object that's going to move at some initial speed u dash in s dash. What is its u in s? So the object, we'll just say the object traces the world line. So we're going to have that dx dash is u dash dt dash. And this is just rearranged from the definition of velocity. Now we're going to sub the Lorentz transformation here in for dt. So for udt even. So that should then be gamma. Oh, so rather sub the Lorentz transformation for each of these. And then we'll do division and then get u. U equals dx dash divided by dt. I don't want to write dx dt because that's confusing. But let's look at dx dash. That's gamma dx minus v dt. And then dt dash is gamma dt minus v over c squared dx. So I think I've got it the right way around this time. That's nice after what happened. Cool. Now we can divide them. So that over that, then u dash is equal to gamma dx minus v dt over gamma's going to cancel. I haven't even written that one in yet. Dt minus v over c squared dx. Which is just, yeah, I'm not even going to bother writing again. It's literally just that expression in the brackets. And we can divide top and bottom by dt. And we should get something useful. So this is then dx dt minus v over 1 minus v over c squared dx dt, which is just u minus v over 1 minus uv over c squared. Cool. This is the relativistic velocity addition that we were after. We can really check this. So if u dash and v, this is the sort of the Newtonian side. So let's say u dash, in fact I'm not even going to write it because I can probably just say it. If u dash and v are much less than c, then u dash v over c squared is going to be a lot less than 1. So u is roughly equal to u dash plus v. Wait a minute, I forgot to rearrange. That's why I'm not plugging things into the right place. You can literally just swap it over. But the minuses become pluses. There we go. This makes more sense. So now if u dash and v are close to c, then u dash v over c squared is much less than 1. So this is all roughly equal to 1. So u is just roughly equal to u dash plus v. That's our Galilean. If we remember, I may have crossed it out vigorously in anger. that it would even be considered. But yeah, if we remember our Galilean reference frames, that's derived from that. And then we need to check the speed of light's invariant, which is fairly simple to do. If we gave a light ray in S dash, and therefore U dash is equal to C, then U is just C plus V over 1 plus VC over C squared, which is C plus V, and then you pull out the C, so it would be 1 plus V over C over 1 plus, sorry, C times 1 plus V over C over 1 plus V over C, because that would be, then that would cancel with that, and yeah. And then that's just C, right? Because the 1 plus V over C counts from top and bottom. So yeah, that's how we get that's how we recover the speed of light, because obviously U then is also equal to C, which is the important thing, because that means U dash and U are the same when U dash is equal to C. So that's good. We're right there. I guess the last thing is that we can't have greater than C. I will write this. So if U dash is less than C, and V is less than C, then U must be less than so U must be less than C as well. So C minus U is C minus U dash plus V 4. Where did that come from? 1 plus U dash V over C squared, which is, and then we can pull the C in, which is going to be C 1 plus U dash V over C squared. No, I'm going to minus it. U dash plus V. What is going on? Why do I keep writing 4s? Oh, U dash V over C squared. Do a little expanding. C over C minus U dash minus V over 1 plus. This should all just be elementary algebra, so I'm not explaining it too much. Again, oh goodness me, 4? Why do I keep thinking 4? Yeah, 1 over U dash V over C squared, and then pull out the V is C minus U dash plus 1 plus V, sorry. U dash over C minus 1 over 1 plus U dash V over C squared. And then I'm just gonna rearrange in there, and that should give us C minus U dash, I forgot the minus sign, that was pretty terrible. It's U dash plus V U dash over C, no, sorry, 1 minus V over C over plus U dash V 4 over C squared. Well, now we can analyze. I think this is a useful form to analyze then. So U dash is less than C, so C minus U dash is greater than 0. V is less than C, so 1 minus V over C is also greater than 0. So we have that these are all greater than 0. Now, this is also greater than 0. We've established that because U dash V over C squared can, because they're both less than C, this can never be C squared. Because they both have to be equal. Yeah, I think that's fairly self-explanatory. They both have to be equal to or greater than C. So yeah, and then C minus U then is definitely, so this must be positive. It's greater than 0, so C is greater than U. Nice. Okay, so that's definitely correct. Now now we start to get into the stuffy stuff, which is interesting. Let's do some tensors, I say. Now what we did earlier, here's a wave equation I made earlier. It was this: squared e x squared minus 1 over c squared e t squared is equal to 0. This, we established, is from x and t to x dash and t dash. This is preserved. That means if we have some operator, and I'm going to struggle to draw squares, but we'll deal with it. What's the best way? I think that's the best way. Okay, this operator is minus 1 over c squared, and this will then operate on some field or something. This is the same in all frames. So what we can ask then, what combination of coordinates is also the same in all frames? Hopefully will give us the space-time interval if I do everything correctly. Let's consider two events. So we have in S, they're separated by dt, dx, and in S dash, they're separated by dt dash, dx dash. Now let's use the Lorentz transformations to relate these two. So dx dash is equal to gamma dx minus v dt, much like what we did above. Gamma dt minus v over c squared. We're not going to do any we're not going to do tensor calculus yet. We will, though, I promise. 4 potentials are coming up. Stick around to see that in some time. I'm not sure how long it'll take. Hopefully not that long. Now what I'd like to do is compute the squares of dx. So we'll do dx squared first. That's going to be gamma squared dx minus v dt squared. And I'm going to expand it for the love of the game. Dx squared minus 2v dx dt plus v squared dt squared. And then c squared dt squared, which is the other term, is going to be c squared gamma squared dt minus v over c squared dx squared, which is gamma squared. I'm going to pull c squared in because it'll cancel with things. C squared dt squared minus 2 v dx dt plus v squared over c squared dx squared. Nice. That was a bit ugly. Still a bit ugly. There we go. And of course we can subtract these two from each other, and it's going to be chunky and horrible. Dx dash. Did I write? I forgot to write the dashes there. Sorry. Dx dash squared. So dx dash squared minus c squared dt dash squared is equal to gamma squared for everything. Dx squared minus 2v dx dt plus v squared dt minus c squared dt squared is 2v dx dt plus v squared over c squared dx squared. Nice. Barely fits, but everything should sort of cancel out now, so that'll be gamma squared dx squared, and factor 1 minus v squared over c squared minus c squared dt squared 1 minus c squared, and that's going to be a multiple of gamma. That should be gamma squared, sorry. In fact, it's 1 over gamma squared equals gamma squared 1 over gamma squared dx minus c squared dt squared. Well, isn't this exciting? Which is, if I could draw an equal sign, dx squared minus c squared dt squared. And so we get that dx, let's make it look pretty if I'm going to box it. So squared minus c squared dt dash squared is equal to dx squared minus c squared dt squared. Terrible box. Yay! This is the spacetime interval. This can be made into 4D as well, but I'm not going to. So then we have this quantity ds squared, which is this dx squared minus c squared dt squared. That's the same in every spacetime interval, and that's really useful. And it shows, or rather, it does something. This operator is the same in every reference frame, and that is shown by the constancy of the spacetime interval between frames. Let's sort of have a look at this, unpack it a bit, because it's very algebraic. So if we have two events with some, with a spacetime interval of ds squared, if that's less than 0, then there exists a frame where this ds squared is less than 0, rather. There exists some frame where the event occurs at the same place. So the proper time d tau, we would say, is the root of minus ds squared over c. That's the proper time between those two events. Then if ds squared is equal to 0, we have this light-like, so only a light ray could connect these two events. That's why c is the same in every reference frame. Of course, if ds was equal to 0, then that would be equal to 0, which would be the wave equation. And then space-like is where ds squared is greater than 0, and that says there exists a frame where they occur at the same time, but there's no causal influence that affects those two events. I hope that makes some semblance of sense. It's only gonna get more interesting, but I am gonna quickly attempt to... Oh, hello. It's not very happy. I am going to attempt to go over very briefly what on earth a full potential is, and what it's just a bit of tensory stuff. So there's a reason why Maxwell's equations require this special relativity. If you write Maxwell's equations in 4-vector form, then they're already Lorentz covariant, which is why we're able to do this. So if we have a full potential a mu, which is phi, if I can write phi over c, and then a, which is our full potential, and then we have an electromagnetic field tensor, which is defined in terms of this full potential. F to the mu nu is equal to d mu a nu minus d nu a mu. It's always the cycling of indices, is it not? That's all that tensors are. We can simplify greatly, and I mean greatly, Maxwell's equations in a vacuum. They become d mu f mu nu is equal to 0. And I think I can just, d lambda f mu nu. I don't think I'm gonna keep it as lambda outside of that. Oh, it's really not happy. No. Stop it. There we go. Oh, why is it breaking? Truly infuriating experience. Right, I'm going to disconnect, I'm going to reconnect, and then we're going to talk about the 4 vectors, because that's riveting stuff. Nice. Hello? Not nice. No. Has it decided that it wants to play nicely? Lambda is what I was attempting to do. Equals 0. Right. These are our tensorial Maxwell equations. This is coding for Gauss's law and Ampere's law, and this is coding for Faraday's law, and I don't know what to call it. No monopoles, magnetic monopoles law. Anyway, when it's written like this, and you kind of have some idea of what's going on, Lorentz covariance becomes kind of obvious. Well, what's happening there is that all the indices are contracted. So these equations are just going to be constant in every inertial frame. What's really crucial here is that the electric and magnetic fields aren't separately invariant. So what one observer would see from like a purely electric field, a moving observer will see a mix of electric and magnetic fields. Since they are simply just components of our electromagnetic field tensor F mu nu. So the Lorentz transformation shows very clearly how they're combined to give you the same reference frames. The tensor representation of Maxwell's equations is sort of really important understanding of, well, I guess the importance of Maxwell's equations, because it shows that electromagnetism, it's almost more intuitive to treat them as the field tensor rather than to separate them entirely and, you know, oh, here's the electric field, here's the magnetic field. It just so happens that they're really closely linked, because or you can simplify and encode better. You can simplify and encode more efficiently information regarding both of them. So yeah, that's nice. I don't think I have much else to say. Hopefully that was somewhat interesting, seeing how we can get these relativistic, very important relativistic principles that Einstein, you know, came up with 100 odd years ago, a few more, 100, 1905 maybe? Oh, I can't remember, he did something in 1905, possibly that. Regardless, yeah, I hope that that's sort of a more physicsy video than usual, I think, because we spent less time doing horrible maths and derivations and stuff, and more time understanding what it actually means. But yeah, I hope you very much enjoyed, and I'll see you next week for something different. Goodbye.